Okay, so compared to the previous topic, right, I would say that this topic is a lot easier. Okay, because in fact, I think this is a lot more related to your secondary school stuff. Okay, because some of the things here, mostly protons, neutrons, electrons, we are basically going to revolve our concepts around that. Yeah, okay, so let's take a look first at the basics. Okay, so we start off slow first, and then later we start to introduce some JC specific concepts. So for the first few pages, we are just going to be looking at recap from secondary school. Okay, so just to start things off, right, okay, you know that atom is made of a few subatomic particles. Let's look at the two main features, right, of these particles first. Okay, of course, you should know protons, neutrons, electrons, right? And out of these three particles, okay, we want to take a look at number one, the relative charges first. Okay, will you tell me what the charges are for these three species? Protons, what are the charges? Again, positive, but here we're going to be putting it as +1. On the other hand, electrons will be -1. Okay, neutrons, we all know that has no charge. Okay, but why is the word relative important? Okay, because again, the actual charge, the absolute charge of a proton and electron is some very funky small number. So we don't want to deal with that number. Just nice, they have the exact same charge, but the opposite direction. So we simplify it to 1. That's why it's called relative. Okay, so the same thing for the masses. Okay, this one will make a bit more sense, right? Because when we look at the mass of a proton, neutron, and electron, okay, in this case, what will you fill in for proton? Okay, 1. Okay, and then neutron is? Actually, neutron is 1. Okay, it's not massless. Okay, what is considered 0 is your electron. Okay, because right, what's happening here? An electron is about 2,000 times lighter compared to a proton and neutron. Right? Okay, but we pretty much simplify that to 0. And what we are trying to say here is that an electron is considered to have negligible mass compared to a proton and neutron. Now, of course, nothing is ever massless, right? Okay, nothing can ever be 0. But in this case, because we are just comparing these three so often, right? We just consider it as no mass compared to the other two. Now, of course, 1 watt is not 1 kg, right? Obviously. Okay, so clearly, protons and neutrons, they have a very, very, very small mass. But just that, in this case, we don't want to deal with that very small number. So comparatively speaking, since their masses are very similar, right, we just call them 1. Okay, and this will help us for later, the word relative. Okay, so you can turn over to the next page. Now, there are some basics that I don't think I have to go through because after all, you did the previous topic, which already has all these things inside. Like, you know, nucleon number, mass number, okay, these two are interchangeable terms. And then we also have the proton number. Okay, in other words, right, this is the format of element, right? Okay, proton number, mass number, everything. This is also considered as the number of neutrons. Okay, and then right down here is the number of protons. The only exception, right, is that in the data booklet, right, the mass number happens to be at the bottom. Don't know why it's like that. Okay, even I also don't know why they formatted the periodic table like this. Okay, but it doesn't matter. Okay, at the end of the day, this is the same as secondary school. Okay, so all the sodium, all that. Okay, we won't talk about that because you know how to read that already. Okay, but what's important here is on this next page, page 4. Okay, of course, you should know what isotopes are, because I already kind of explained that in the previous lesson, previous topic. Okay, but more or less, you need to remember the difference. In your first few class tests, right, or lecture tests, there will be simple questions like these where you need to get the marks. Yeah, okay, easy questions like that, I cannot forego one. So all these like same number of protons, same number of neutrons, different number of neutrons, you can't go wrong with this. Okay, so yeah, definitely places to get marks are here. Okay, as you go on more into J1, right, this kind of simple questions will just start disappearing. Okay, because they are not so easy to get marks really. Okay, and we explained the idea of isotopes in the previous chapter as well. Let me just recap that. Okay, the most common example of isotopes is probably chlorine, right? Now, of course, can you remember chlorine's mass number in JC? What is it? Yes, okay. Today we'll be dealing with 35.5. Why is there a decimal place? Because we take the watt of these two. Not the average. Remember, I introduced a new word in front, right? Not just average, but okay, kind of similar. Okay, we call them weighted average. Okay, because we know average just means you take both of them and you divide by 2. You add them both up, divide by 2, right? But you can only do that if both proportions are equal. Okay, good. In this case, that's not the case in real life, right? Okay, because there is a much higher chance of you finding fluorine 35 than 37 chlorine. So in other words, right, the final answer is should it be lying more towards 35 or 37? 35 because you have a greater weightage. Okay, so that's the idea, right? Behind this thing that we went through the last topic already. Okay, there are many types of common isotopes. The other one more commonly you will see is deuterium, which is your 2H. It's just heavier hydrogens, right? Okay, so that's the rough idea there. Again, so we're kind of squeezing through the first few pages. If there's anything you finally need to clarify, right, you can also now, because eventually all this is going to be part and parcel of our basic. Okay, then if you look at page 5, okay, also not much, because page 5, we are looking at ions. You should know cations and anions by now. Okay, I think this is quite basic stuff. Okay, usually this is the introductory topic, that's why it's more in detail. Okay, and with that said, right, okay, you can take a look at page 6 first. Page 6, just fill in all the number of subatomic particles. It's right after this page, right, where we'll be looking at the actual new concepts in that sense. Okay, so you can quickly fill this up first. Yes. It's not right. We did grow you get this? Yeah.
Oh, yeah, because of the double angle.
Yes.
That's what we're gonna ask. Okay.
So it's not half, right? Integral of cosecant squared.
Okay.
You don't know how to integrate. First row of 14, right? Second one, 31, 28, 39.
Yeah.
What is this? 15, 18, 16. And, okay, so before you flip to the next page, right? Okay, we're gonna not spoil whatever that's coming to the next page. Because I want to try, we will try to come up with the idea of the next page together. So there's a lot of space on this page, right? You can jot down whatever.
Yeah, very similar.
But essentially, we're going to introduce a new concept and called angle of deflection. This is something is an add-on to whatever you learn in secondary school, right? But let me just present a scenario. So just imagine, right? You have an electric field. Now this electric field has a positive plate and a negative plate. Not to worry, there's no physics stuff involved. Okay, but what's important here is I ask you a simple question. If I were to place a neutron, right, and let it travel through this electric field, how does the path of travel look like? Okay, it's just a straight line. Why do you say that? Okay, good, correct. Okay, so a neutron doesn't have a charge, so it's not going to deflect to any plane. But now, let's come up with a simple question. How about a proton? If I were to put a proton through this thing, where will it deflect towards?
Oh, yeah.
Proton. Okay, proton attract towards the negative, and then electron will deflect towards the positive plane. Okay, so before we draw the path of travel for these two species, we are going to take a look at some of the properties that we've learned about protons and electrons first, and see how the path actually looks like. Okay, clearly it's probably not going to be the same line, right? Now, first of all, if you take a look at their charges, protons and electrons, okay, they both have the same charge, right? They are both 1. So the only difference is the direction. Okay, so the direction you already know is on opposite directions, correct? So the charge here, not really my concern. But I want you to take a look at their relative masses. Could you just look at their masses, right? And then just predict which particle will deflect more? Okay, the lighter one, obviously, right? Okay, so this is a very intuitive idea. Okay, electrons are 2,000 times lighter, so that's going to affect its angle of deflection also. Clearly, the angle of deflection here must be greater or smaller. It's greater, right? Okay, because here, electron will be very, very curvy, basically. Okay, the curvature is very large. Okay, but you need to draw this yourself in exam also. So the next thing is your proton. It's curving towards the negative plate, but as you can see, the curvature is a lot more gradual. It's not as sudden and not as sharp as the path of that electron takes. Okay, and this is something very commonly shown in exam. Now, of course, your examiner won't actually go and measure the angle with a protractor. You also don't need to do so. All that's important is I need to be able to look and I'll see that the angle of deflection is clearly very different. The examiner needs to be able to see that also. So there shouldn't be any doubt in your drawing. Okay, so that's a very simple idea. That's what we're dealing with right now. So aside from the drawing, right? Now let's take a look at what we considered before we came up with the path. Number 1, the charge. If you think about it logically, right? If you have a larger charge, right, would it be more attracted or less attracted to the plate? more attracted. Okay, good. So if it's more attracted to the plane, is the angle of deflection going to be higher or lower? More attracted, so it's very, very sharp, right? Okay, so the angle of deflection higher. Good. Next, we have mass. If the mass of a particle is larger, is it more easily deflected or less easily deflected? Okay, clearly. Okay, so clearly less heavier masses are just going to affect the half of deflection. And because of that, the angle of deflection is lower. So by taking a look at this very logical process, right? Okay, let's determine a relationship. Charge and angle of deflection. What is their relationship? One go up, the other also go up. So you describe them both as being, what's the word for it? Good, proportional. Okay, so in other words, for Q, you are directly proportional to your theta. Then of course, on the other hand, if you look at mass, what's the relationship? Okay, inversely proportional. Later on, some of our calculations will be looking into this. Okay, you have learned inversely and directly proportional in secondary school. JC is not much more different. Okay? So we have learned this before in terms of, I think you learned this in math. Okay, where we have y equals to kx, that's for directly proportional. And then you have y equals to k over x, that's inversely. JC is similar. Okay, so let's come up with an overall relationship. So clearly, angle of deflection is affected by two different factors. So what is the overall relationship here? The angle of deflection is directly proportional to the charge, but inversely proportional to the mass. So this is like the main and the only thing they need to know, right, for this entire section. The angle of deflection formula is just this. So the reason why I don't want you to flip over to the next page just now is because I wanted to just guide us through this to come up with the expression of. Okay, then at least you would just don't you won't just blindly memorize it. Yeah, okay, so once that is done, you can pretty much turn over to the next page. Okay. And just a small little clarification, right? Okay, this right here with the little ribbon sign, right? Okay, this is known as relationships. And just a small little pointer, take note. This is not an equation nor a formula. Now, it's obvious as it seems, right? Okay, the reason why I have to clarify this is because too many instances, I have seen people try to use this to sub in values. But that doesn't make sense because it's not even an equation to start things from. And since it's not an equation, this can allow me to only compare the different factors, but I can't actually sub values in. Later, you see what I mean when we do the question. Okay, but any issues so far? Okay, so we are basically on like the page 178, okay, around that. Okay, for question, look at page 8. Okay, whatever on page 7 we covered together already. Page 8, just look at that question first. Okay, so this is a qualitative question, you need to explain yourself. Right, okay, so just take a look at this question, right? You just verbally, just maybe tell me, right, how will you answer this question? Okay. Okay, so.
Electrons are more easily
Okay, so there's a greater angle, all that. Okay, if you were to write that, right, unfortunately, you will not get the full credit. Okay, because, right, if you look at the relationship we have established, you have only talked to me about your mass. But what about the charge? Okay, even though the charge is the same, right, you still need to make a mention of the charge in your answer for the full credit. So that's like the pattern you will see in JC also lah. Okay, so first of all, the charge of an electron and proton is the same. I just use a tick to denote that. But an electron is a lot lighter. End up, your angle of deflection is much greater. Okay, good. So you must tell me about it. Okay, so let's write down a sample answer.
You do this?
Yeah, I did that already. But I remember doing the extra plus one.
There's no points on this, right?
Yeah.
Extra plus one is separate from the fraction. So then what you have is just a plus 2 integral 1 over.
Oh my god.
Okay. Okay, so that's why I say you always must have the left right.
One more thing you can also say, right, is same relative charges. Okay, so again, they don't exactly have the same charges. But what's important here is that your electrons have a lighter mass. You don't need to say lighter relative mass. It's a bit redundant because objectively, electrons are light. Okay, so it's about the charges that's a bit more tricky. Your choice of words here must be more careful. Okay, so it doesn't matter about the sign. The sign only tells you the direction at which it reflects. Okay, but overall, it's still just the magnitude. Okay. Yeah, okay, we'll be doing more explanation questions on the next page. Okay, so you can take a look at the next. Okay, so take a look at page 9, right? Okay, we're going to try this first question together. But what I need you to do first, read through the context and then just try part 1. Okay. So, good answer. Yeah, how do you know negative? Deflection is positive. Oh, okay, because you saw the 4 degrees and 2 degrees. Okay, so that is not the best way to tell whether it's negative or positive. Okay, because right, if they can say deflected by 4 and 2 degrees, but they never say in what direction. Could it be the positive direction or negative direction? We are not very sure. So the question will never say they both deflected by -4 and -2. Objectively here, they're just saying the number, the degree in which it deflects by. So there's a much more conclusive way to determine, right, whether it's plus or minus. Now, first of all, if I were to tell you, right, one hydrogen atom, let's just list down, right, all the subatomic particles in this atom. Okay, can you tell me how many protons, neutrons, electrons? 1 proton, okay, what else? Okay, the proton number is 1 also. Okay, 0 neutrons and 1 electron. Now, okay, if you take a look, what's the overall charge of this hydrogen atom? If it has 1 proton, 1 electron. Nope. 1 plus, 1 minus. Okay, so it doesn't matter whether they're neutrons or not, because they don't affect the charge. Idea is 1 plus, 1 minus cancel out, right? So if I were to put a hydrogen atom through the field, it's just going to go straight. But why is it that it deflects towards a plate in this case? Did they use the word atom in this question?
No.
No, what did they use instead?
Nuclei.
Okay, nuclei or plural for nucleus, right?
It's too
Why?
long.
What's the difference between atom and nucleus?
Yeah, I agree.
Doesn't have electrons.
Exactly. Okay, so in this case, if they say 1 hydrogen nucleus, it's only 1 proton and 0 neutrons. So what is the overall charge of this nucleus? It's +1. Okay, so that's why, right, this is a very tricky question, because over here, right, usually people just skip through the word nucleus. They think it's not important. Okay, but it's different from atom. So I suggest you can write down the atom also, and then just include. Okay, this one have electrons that one don't have. Okay, then I can include at the side or something. So if I want to do the same thing, right, for your helium,
Your building is where?
Yeah, over here, then I put the date as well. It's all wrong. Yeah. Wrong really.
Yeah, put in +2. You're going to re-extend it. I don't think you get very well. After you did it.
Okay, for helium, I'll just tell you what the proton number is first. 1 is at
25 here. Is it the free? 你实在。
Okay, +4 is the charge. It's not actually, because here how many protons and neutrons do you have? Okay, so 2 protons, 2 neutrons. Okay, so the charge is only 2. Okay, 2. Okay, neutrons do not contribute to any charge, so you can pretty much ignore it. Yeah. Okay, but either way, right? Okay, if it deflects, if both of them deflect towards plate A, so that means what charge is it? Okay. Oh, plus 3. No. Okay, it's a negative terminal. Okay, so good. Okay, so with that said, right? Okay, you can take a look at part 2 also. Part 2 is explanation. So I suggest, right? You can take out your formula first, your relationship. This thing over here. What you do next is just compare the differences between both of the factors. So charge compare it. Mass you also compare. Then later the explanation we can further it out again.
Yeah. Okay.
I don't know that method though. This method is another method. I don't use this method. Actually. You know? So
Yeah, I got it.
you know you don't have a separate.
Which formula you use for the
What do you think?
This one and first one.
Yes, what is A squared plus X squared? X squared.
But 2 can be.
Perfect.
Oh, okay.
Not bad, sir.
Not bad, right? You know what the smell? It reminds you of anything. No. No, no. You let her smell?
What? What does it remind you of? Lavender.
Toilet.
Facts.
Actually, it's supposed to be iron water.
Oh. Yeah.
I don't know.
Now they say. They put it in the aircon.
In the aircon.
They put it in the aircon, that's so strong.
Oh,
Right.
So we put in our aircon also.
Already. It's smelly. Yeah. Oh, how is your community service elective? Very cold. Like physically cold. Or they are cold. Okay. So basically they ask you to pick apart existing projects. Why? I thought they're like asking you, oh, you're like help. Oh, wait, are you forced to do a project in this? No, never mind, won't do, no need to do one. Last time I never do. Oh. No, but you don't have to start one. You can just join one and get some points there. No, that one because it will pick up time. Or it's already ongoing lah. Right. Oh, okay. This year one just be careful.
Yeah.
Because it will be quite hard to manage your time. Yeah. Oh yeah, you decided already. What CCA have you decided? Oh, is it the team? Right. Oh, wait, that's sick. That's quite funny. Oh, not bad. Okay, then you can focus on your thing. Okay. Fair enough. No. Oh, yeah, sport outside.
How can I get it?
What? Oh, gym. Okay, like you said before, like there's no gym in Haram.
Oh, wait.
So you have to do. Oh, but is the commitment still not very high, right? Tired. Once a week, okay lah. Once a week, okay lah. Not so bad. Yeah. Times a week. You once did gym for 4 times a week for competition. Is it? Customization. Oh,
So like if you get presentation, you don't need to do like 3 hours only.
where got all this part of the RGS curriculum? Yeah, why so weird?
Every 2 weeks, you get 5 hours on.
Yeah, because you want to introduce it, yes. Just like you got the plus.
Every week you must fulfill 5 hours or it's just it? Oh, okay.
PE, recess, aesthetic, yeah, you go.
Wow, sure. Wow, but wow, I didn't know got such thing. They actually want the holistic nonsense, right? Oh.
We have the blocks. Okay.
Uh.
Like, so the state that's how you elected or like,
Wow, electives and all that. Okay, not so bad. Wow, what are you doing? Who are you helping? Old people, children. Wow, it's always old people, children, or migrant workers. Yeah. Or that one I think are the most check on honestly. Special needs. Because legit not easy manage. You don't actually know. They don't need
Question 2, right?
Yeah. Migrant worker, like even the migrant workers get tired of all the students coming to them. Because they know that nothing's gonna change. I know last time the one thing that they make the soap with the migrant workers.
So what to do for that?
How about the okay? Yeah, that actually, I don't know how you're gonna do that. The school, yeah, because I went to the Philippines.
Okay.
$7,000 again. One ticket is about, right? You can bring only three. I don't know, 120, right? Okay, not so bad. It's very bad, very bad. Dealing with funds is tough. How they never you don't know how to beat. No experience.
Yeah, it's like
Yeah, I never do all this before. So I thought CIP or in JC I don't know if so there was a phone. I just attend like this, that I didn't want to start one because I knew I'm not gonna manage part time role. Yeah, but it's not a lot of there's like continuity, right?
yeah.
Why not you pass it down to the next? Oh, but you're still hating the project.
No, I don't.
Okay, that's quite respectful. You can write down the answer for this first. But before that, how you work out the answer? There are a few ways. I'll show you one way first, which I think you should use in basic because it's a lot faster. You can take out this formula, right? And number one, right? That's what a lot of people will do this. They take a chart. Okay, starting values into a relationship. Okay, try not to do that. It's just wrong. Okay, so what we're going to do first is from the perspective of the question, they say hydrogen is twice that of helium. So look at hydrogen now. What is hydrogen's charge compared to helium? It's a comparison thing, it's half. Okay, so you should multiply by half here. This is what I can do. And then how about the mass of hydrogen versus helium? Comparatively, hydrogen is how many times lighter?
3 times.
Okay, not 2 times. Because you have to look at the mass number. The mass number of helium is 4 times heavier. So conversely, hydrogen has to be 4 times lighter. Now, why is that the case? Because if you remember our relative masses, right? Protons and neutrons have the same relative mass. So it's considered 4 particles. But this one only have 1 proton, so it's considered 1 particle only. You can see that? So you have to be looking at the mass number. So if you take a look, if it's half on top, 1/4 at the bottom, half divided by 1/4 will give you. It will give you 2 times. Okay, 0.5 over 0.25. So in other words, this is one way you can work out your answer beforehand first, before you actually go and write down the full thing. You don't want to write down the full thing, then have to erase this and erase that. Okay, another way you can work this out is via the secondary school method, which still works. Remember y equals to kx, right? Okay, we can turn a relationship into an equation if we include the k constant. So what's happening here is I can manipulate this into k times q over m instead. See that? So I just introduce equals and k inside. Now, by doing this, there's a more numerical approach. Here you can actually suck in the actual values without the comparison. So what do I mean by that? For hydrogen, the angle of deflection is k times, what's the charge of hydrogen? 1. The mass is also 1. So basically, theta equals to k, and theta, the angle of deflection they told us is 4 degrees. Can see that? In other words, k is equals to 4 here. But I can repeat the same thing, right, for the next one. For helium, what is the charge? K2, and then the mass is 4. In other words, we simplify this, this is half k. And since we know k is equals to 4, half k is equals to 2 degrees. Okay, so that's why it works. But this one, right, is mostly for calculations. I still recommend this method instead, because you are comparing instead of doing them individually one at a time. So even though this works, okay, let's take a look at our answer first. So number one, you want to tell me, right, okay, that the charge of the hydrogen nucleus is half of or half that of helium nucleus. Good. Then you tell me about the mass as well. Okay, the mass of a hydrogen nucleus, okay, is 4 times smaller. Okay, sometimes you cannot use a nice word like quadruple, right? You can say 4 times smaller than that of helium. Okay, okay. Okay, then finally you can just make your conclusion. Your conclusion is your angle of deflection. Thus, angle of deflection for one hydrogen nucleus is 2 times larger. Then finish. So yeah, the explanation itself, right? I know it looks long, right? But honestly, it's just you describing each factor and rounding it up with your angle of deflection. That's pretty much. Yeah. Okay. And then finally, okay, we can take a look at part 3. Part 3, they ask us to do calculation for a separate species, a species that we haven't seen yet. Okay, the species here is 3 helium nucleus. Now the thing is, the clue that I'm going to give you is, let me try the question, but it is whatever that I mentioned just now. You cannot sub in any values to perform calculations on the relationship. You can only make comparisons. So we must convert it to an equation, right? How? K and whatever. Yes. So use the equation and then you can calculate your answer. Yes. Remember that an isotope always has the same proton number. Okay, so in other words, no matter what, you want to identify the identity of an element, right? Which one is more reliable, the bottom number or the top number? Always the bottom number because it's always the same. Okay, so 2. I'm seeing Chloe tomorrow. Did he tell you that she's coming back? Yeah, she can eventually join you also. I have to catch her. Sorry? Oh, you know Ariel too. Oh, yeah, I contacted her also. Oh, I didn't know you all know each other. Oh, okay, okay. Your previous CCA lah, right? Oh, you gym. Oh, do you tell her to come along also? All right, I think it's
First, and then no.
really. Why? Oh no, your 10 years of friendship, she doesn't listen to you. What the heck? Oh, that's quite funny actually. Oh my gosh. Oh, okay, okay, I'll be seeing her next week also.
Yeah.
Oh, okay, good.
They said initially.
10 years of friendship. I only have one friend I know of. By now 14 years. Wow, that was a bit too much. Well,
I think 2, but then the one other.
oh, okay. Because I know someone said, right, if you know someone for 7 years, it's gonna be he or she's gonna be a lifelong friend. I think quite true. I don't know. What's going to be playing the game? X. Can you find the universe? Can you you have moments 8 over 3, yes, basically, yeah, 2.67 degrees. Okay, for chemistry, you can, I think angles in math, they say 1 degree, right? But chemistry doesn't matter, just 2s, 3s have chem. Yeah, okay, good. So it's basically using this formula. And I just want to just mention something about K. Now, as you perform the calculations for this question, K is the same or different? Same, right? Okay, because say secondary school, they only teach you guys that K is the constant. Okay, fair enough. But what does it actually mean, right, in the context of this question here? Okay, so perhaps you can take this down. K is the same because we are passing through the nuclei through the same electric field. So in other words, if you are performing the experiment in the same conditions, essentially the electric field strength is the same, then K, the proportionality constant, can be kept the same. Okay, so same electric field. Now, sometimes the question will not explicitly say it's passing through the same field, okay? Or sometimes the question will just say under the same conditions. If you are passing through under the same conditions, you can assume that K will be the same. So it's not just a random thing in this case. So for example, if let's say the question says they pass through a different electric field, then that's where you know you cannot reuse the K that you used for the previous calculations. I've never really seen it happen because they don't really make this overly complicated, but just as a precaution first. Okay, so in other words, okay, with that said, right, you can pretty much do 2 and 3. The angle deflection, we've pretty much covered the whole thing already. So 2 and 3 is just practice. Okay, so we'll give you a bit of time to just calculate these two parts. Part 2 is to explain. Good. Yeah, if you opted for the K method, okay, and also I show you the alternative method, which is just to compare the relationship. Okay, so good. Okay, you should be able to get the answer. Okay, but for question 2, okay, just make sure that it is okay because you use the K method, as you can see, you need to do 2 steps, 2 sets of working. So it might be a bit long in exam, not very optimal. So let's just try to get used to this relationship method. Okay, again, it is similar, but here we're comparing between 21H plus versus 11H plus. What is the charge for both of these cases? 0. The charge here is right here, +1. Okay, so you have to compare the charges here. Okay.
Is it 1 -1?
-1 equals, what do you mean by that? Okay, so I think let's list down the number of subatomic particles first. How many protons are there here? How many electrons are there? Okay, here is 0 because you have 1 less. So the fact is, if you have 1 more proton than an electron, right, the excess charge is still +1. In other words, you don't actually need to count the subatomic particles, unlike the first scenario here. Because here they mentioned nucleus, that's how you need to count. Here, right, from now on, whenever you see anything regarding charges, you just have to look at the ions charge already. So here, very straightforward, both cases are they have the same charge of +1. And since they have the same, let me just put a tick over there, note that they are the same. How about the mass? The mass of this guy compared to this guy is double. Okay, if you have double the mass, same charge, that means your angle of deflection has to be half. Okay, good. So that's what you can explain in your answer. Same relative charge, twice the mass, so half the angle of deflection, 3 points. Okay, in exam, okay, we will slowly learn how to make our answers more concise, and that's how like one step towards that. Okay. Okay, so now that you know that the charges, you just need to look at the cation ions charge, right? You can try questions. Okay. You know the problem. What is it?
Put there. Oh, this one the comment.
Oh, I only buy for all the food. It's all down. I think they have like sauce everywhere.
So that look
What do they sell? That is,
also big.
But not only
country band $9.
Yeah, it's a little bit.
The plates. The plates. Box.
Lifespan approximately 4 months.
I just realized I'm going to date for your shirt.
Okay, bring us a nice video.
It's a man.
It's gonna be dark.
He's going out on that. You assume it was a woman.
The problem is
You made assumptions.
you made incorrect assumptions.
I guess I'm gonna do it.
So the answers on the top right should be 22.5. That's the error you're working. Okay, so that might be checked first. Okay, they gave us all the information for Helium, right? The Helium 3 plus. So if we take out this formula over here, theta equals to K Q over M. For Helium, they told us that the angle of deflection is 10 degrees. We don't know what K is. That's what we want to find first. Okay, because they're both in the same electric field, assuming, right? The charge in this case is what? 3. What's the mass? It should be 70, good. In other words, your K here, just type in the calculator, it should be about 233, around there. Right? Okay. Then the next thing is you try to find the same angle of deflection for phosphorus. Okay, so for phosphorus, now that we know what K is, right? 233.3, you can sub everything inside. What's the charge for phosphorus? Okay. If you want to put the minus there, actually also can. Okay, let's just try it. If you don't put it there, also never mind. Because for angle of deflection, they don't really care about the sign. Okay, it's not a requirement. What's the mass?
31.
Yeah, okay, 31. And I think you might have just typed into calculator wrongly or whatever. Okay, here you should get about negative 22.6 degrees. If you don't put the negative sign, it's fine also. But if you do put the negative sign, it makes sense because 10 degrees, you assume it's positive. Negative 22.6 is in the opposite direction. Why opposite? It's because they both have opposite charges. So you want to put the negative there, up, go ahead. Okay. Yes, very nice. Okay, good. Okay, so we have just conquered the first new concept, angle of deflection. I don't think it's very tough because it's only one expression for you to play around with. Okay, the next thing we're going to discuss today is the structure of an atom. So you can flip over to the next page. When we look at the structure of an atom, right, okay, what we mean is how do you picture an atom in your head the first time you think of the word atom? Okay, so most of us will have the same picture in our head, right? Which is that when you think of atom, you think of the nucleus in the middle, and it's surrounded by what? Okay, all the shells first, right? Okay, so that is what we normally picture in our head. We have this nucleus and we have many shells. Now, is there a special term for these shells? You guys probably just call them electron shells and most, right? But yeah, in JC, right, there's gonna be a lot more detail towards a structure of an atom. This shouldn't be our image in our mind already, because this is technically not enough. So I'm just going to break down how the atom should look like. Okay, so it's kind of like a flow chart. You want to write this down somewhere also can. Okay, but basically, instead of calling that shells, we actually call them principal quantum shells. Or quantum shells for short, because I'm a bit lazy. I don't want to write the word principal. It just sounds cheap only. Okay, but at the end of the day, this is still a shell. But before I move on to anything else, right? Do you remember what is electronic configuration? Like for example, if I were to give you chlorine, right, 17 electrons, how will you express its configuration in secondary school? Oh, you all do SPDF already. Oh, okay. You all skip the T. You all do SPDF notation, right? Have you all done the 2.8 notation? Okay. Okay, you all have done the notation, right? Okay, because generally that's what most people are taught. You all IP, so they teach you something like it. Oh yeah, I remember already. Last time I IP, I also did SPDF. Okay, never mind. Okay, so that means you should be a bit more familiar with this stuff. Okay, but last time, right, okay, more conventionally in O-level stuff, they use 2.8.7. They have never learned SPDF. Okay, but yeah, here we're going to learn SPDF there. We're going to recap what all those SPDF notation is like. But first of all, you need to know quantum shells come first. Then after, the thing is, a quantum shell can hold a maximum of 8 valence electrons, correct? But the thing is, this one too big already. So we have to split them up into multiple subcategories. Okay, but first of all, quantum shells is denoted by a number. Very simple. The first shell, second, third, fourth, and then it just keeps going outer and outer. Right? Okay. Now, the thing is, you can think of the analogy as like a school. Is it possible for one teacher, right, to teach one entire school of students? No, impossible. Too many already, so you need to split them into maybe perhaps levels, like Sec 1, Sec 2, Sec 3, Sec 4, right? So what we're going to do now is to split them into this thing called subshells. And let's just recap all the notations. Subshells are not used number. We don't use numbers to denote. We use S, P, P, and D. We will ignore F still. Okay, JC will still not touch F. That one too complicated. And when it comes to subshells, right? Okay, we are basically splitting it into smaller types of shells that hold less electrons. 8 electrons, once again, is too much to count at once. So we just look at 6 or maybe even less. Okay, so first of all, subshells, we got 3 different types. Let's list down all the 3. So we have the S subshell, we have the P subshell, and D subshell. Only need to focus on these 3. But yet, right, it is actually still not enough. We can still zoom in even more into an atom, right? And we can still find more subcategories. So what do we call the next thing? After a subshell inside has orbitals. So in an S subshell, just pay attention to the naming convention here because it's a little bit confusing. An S subshell has an S orbital. Even though they're the same name here, later on it's not the same really. A P subshell, you can find 3 different orbitals. The PX orbital, the PY orbital, and PZ. The X, Y, and Z, right, simply represent the fields. So of course, we live in a 3D world, you're going to see 3 different dimensions, X, Y, and Z, 3 different axes. And then finally, for the D subshell, right, you can actually come across 5 different types of orbitals. So orbitals are like a smaller unit now. And let's list down all 5. dxy, dxz, dyz, okay, and then continue, dx squared minus y squared, dz squared. As complicated as this looks, right? Have you learned this in secondary school before? I don't know whether they taught you the orbitals. They only taught you guys up to P. Okay, so you guys know what subshells and orbitals are, basically. Okay, so that's good. Okay, but let's just list down all the numbers and break down again. It looks a little bit messy already. Okay, but essentially, an S subshell can only find 1 orbital. A P subshell has 3 orbitals. D subshell has 5 orbitals. Kind of like a 1-3-5 pattern, very simple here. And we can still dig deeper. Okay, basically you can imagine now, you take your phone screen, you keep zooming in, right? This time we keep zooming in, we can keep finding more and more things. So if the most zoomed out version is quantum shells, which are your normal shells, you zoom in is sharp subshell, you zoom in even more, you can find orbitals. And then after you zoom into the orbitals, that's when you can find your electrons. Okay, in the O-level syllabus, right, electrons can be found here, which is not true. So let's look at the rule first. No matter what kind of orbital, what kind of weird name it is, right? An orbital can hold up to a max of 2 electrons only. So no matter what the name of the orbital is, you must know orbital is so small to the point where it can only hold 2 electrons. Make sense? So you zoom in into the smallest unit. So if the S orbital can hold 2 electrons, the S subshell can hold how many electrons? 2 also, right? If the P orbitals can hold 2 electrons each, a P subshell can hold up to 6 electrons. And then a D subshell is 10 electrons. Very obvious. So that will explain, right, a lot of the electronic configuration later. So I still have the old configuration of chlorine, which is wrong. We will not use this anymore. Too easy. Not specific enough. So this right here is kind of like a breakdown, right, of our atom, basically. Okay, an atom, you can find all these different things. So, okay, so far. Right, okay, so it's good that you've learned this in IP. A new student will be super lost with this one. Okay, so you can turn to the, okay, a lot of the stuff has been mentioned already, but on page 12, okay, this is important, of the previous page. Okay, page 12 at the bottom over there. Okay, so we are going to know how to draw the shape of all these orbitals. Okay, orbitals, they have some sort of shape. We start with the P orbital first. A P orbital, you must know the name of this shape, which is called a sphere. This is spherical in shape, not circular. If you say circle, they will mark you wrong. Why is that the case? It's because okay, it is also known as a 1s orbital. It is a spherical shape. Now, spherical is a 3D shape. So in order to express a 3D shape on a 2D piece of paper, we must draw the 3 axes to denote that. So if you just draw a circle and you forget to draw the axis, they'll still mark you wrong. Okay? Now, if you were to have a 2s orbital instead, is it bigger or smaller? It will be bigger. This one is quite common sense. It just keeps on getting bigger and bigger. Okay? Next, a P orbital has a different shape. p orbitals have a dumbbell shape. A dumbbell shape is just a number 8, infinity 8 lah. If it's the px orbital, where do you think the dumbbell shape is going to lie? X, Y, or Z? X, or Z, simple as that. Okay, so for X, right, okay, you can just lie the letter, the number 8, sorry, okay, on the X orbital, on the X axis. Okay, so it's like kind of a satay stick sticking through the orbital. Okay, and then this is px. Okay, same thing, the larger the number is 2px, 2px versus 3px, which are larger? 3px. Okay, why is there no 1p? Okay, because kind of never thought about this just now, okay, but let's mention in the first quantum shell, you only have S. In the second quantum shell, what do you have? S and P subshells. In the third quantum shell, you have S, P, and D. So 1, 1, 2, 2, then 3, and 4, 3. You don't look at 4. Okay, 4 go all the way up to F. Okay, but that's the idea here. 2P versus 3P. 3P is going to be bigger. Okay, then the next thing is, of course, for p orbitals, very simple, you draw the 3 axis, right? But you just need to highlight it on the y axis. Make sense? Okay, then you draw the z through also. Now I would say that whatever that I'm drawing right now, these are 3 marks for you in the exam. In your first few lecture tests, you will be tested on this, and I can tell you, right, this one definitely easiest score because you are just drawing. It's not that hard to draw also. So you have learned up to P, right? Okay, but the issue is D. D can be quite complicated and it wouldn't make some sense to you sometimes, right? Okay, but they can test, and if you do study, right, it's quite work to get. Okay, so let me just highlight this to make your life a bit easier. I would like you to group all the doubles together, all the pairs together. You don't need to group them, but you just need to take a look at the orbitals in your books. I'm not going to draw them out because it's a bit long. I want you to notice about these 3 orbitals. Can you see, right, that all these 3 guys have a little shape that looks like this? Kind of like a double dumbbell that has the shape of an X. Now, first of all, you see all these lobes. Okay? All these dumbbells are called lobes also. Are they lying on the axis? Are they lying on the axis or between? Between 2 different axes, right? Okay, that's why they come in pairs. It's not that they lie on the 2 axes. They lie between the 2 axes. So you just need to remember that. Okay, and then the second group I'm going to write in blue is the one with squares inside. Okay, but first of all, can you see why there are these 3 categories, these 3 combinations? X, Y, Z, you can like pair them up 3 different ways. So X, Y, X, Z, then there's Y, Z, right? Okay, so that's the only way. And then the next one is whatever with squares. These 2 is another group by itself in blue. Because I want you to take a look at the orbitals, right? And then just tell me, how do the lobes work? How are they positioned on the axis? Just now that one is between 2 axes, right? But this one is like literally along the axis. Okay, so for these 2 blue colored groups, okay, the lobes pass through along the axis. Which axis? Okay, you can see whatever, when you see a square, you just pass through along. X square minus Y square means you pass through X and Y lah, obviously. Okay, as for Z, I just want you to notice something. They pass through Z, but there's a ring in the middle. Okay, that one not typo or anything. Okay, that little donut in the middle you must draw also. Okay, again, there's no rhyme or reason, right, as to why there's a ring inside. It doesn't matter. Okay, they'll never ask. Okay, but yeah, these subshell, these 5D orbitals quite important. And so far. Again, no matter what the shape, you can only hold 2 electrons each. Again, the axis can be positioned whatever you like. But the reason why I like to position it like this is because x-axis and y-axis is your graph mark. Okay, the z-axis will just be the third one passing through. Okay, but you can label any axis you want. Because no matter how you rotate, like you notice we are in a 3D world, right? Anything can be interpreted as x-axis, y-axis, or z-axis. Okay, but we define it as this like that. Up to you. So, okay. Any questions so far? Okay, so this one is okay, right? Okay, we take a look at the next page. Okay, the thing is you have learned how to do your 1s2, 2s2, that thing, right? Okay, so it's not that bad yet. Okay, we can still remember some of the principles. I don't really need to go over all these rules. But basically, the rules here, all these Akbao principle, Hans rule, you don't need to memorize their names. You forget about them and it's definitely fine. You'll never use this ever again. But for Akbao's principle, right, you just need to know the order. Okay, it's 1s, then 2s, then 2p, but you should know the order by now, so shouldn't be a big problem. Okay, Hans' rule just says this. There's this thing called electron box diagram. Have you seen that before? Okay, so if you want to fill in electrons in a box, right? Okay, they have to fill in singly first. So you can't pair them. Singly first, then double. Do you know what the reason for that is? Okay, any idea? Why do electrons want to stay single, right? Rather than getting paired? This implies that electrons, do they like each other? They want to be alone, right? They want to be left alone. They do not want to be paired with something else. Which means what? Why do electrons want to be left alone? What's so bad about them getting so close to each other? They will repel. Okay, electrons have the same charges. Putting them together will cause repulsions, which makes the overall atom or whatever very unstable. Good. Okay, that's why they want to be left alone first. If there's no choice really, right, they're all singly filled, then you can pair them up. Okay, so that's the idea behind Hans' rule. Okay, for Aufbau's principle, you just need to follow the, if you for some reason forget the order, right? Just look at the arrow going like diagonally downwards. Okay, and then you can just follow that order. Yeah, okay. Then we take a look at the next page. Okay, the third rule is some guy called Pauli. Don't know who this guy is. His exclusion, don't know what lah. Okay, but later this one will go over again. Okay, electrons must be of opposite spins. Now you don't know spins because you wouldn't take this is in physics and you don't take this in JC, and it's something completely weird that I also don't really understand. Okay, that one physics really. Okay, but it doesn't matter. Okay, that one we look at that later on. As for electronic configuration, can you look at potassium? Potassium is your K, and I just need you to kind of fill in the configuration for 19 electrons. Okay. You might want to confirm. Okay, let's confirm the answer here. Okay, so how do we express 19 electrons? Okay, we start out with 1s. Okay, so I kind of need to explain because for the sake of Hula also, she O-level, so she don't know how this works yet. Yeah, so it's completely new. Okay, but anyways, just for the sake of the recording. Okay, so for 19 electrons, right? 1s, you must fill it up with 2 electrons because the s represents the s what? Okay, it's S subshell in this case. Okay, later it will look more clear lah. I know S subshell and S orbital use the same names. Okay, but you can see they are kind of equivalent because they only have one orbital. Okay, but here the S represents the subshell, the 1 represents what? Yes, the first main quantum shell, basically the one that's right beside the nucleus, the closest. But after 1s, if you follow the Aufbau's principle on the previous page where it goes diagonally downwards, the next one in line is 2s. This order eventually you need to memorize. And memorize really, right? Okay, then afterwards you'll be very, very easy. 2. Okay, but for 2s, what is the number on top? 2 also. Okay, because s still stands for 2 s subshell, you can only hold 2 electrons. After 2s is 2p. Okay, so if you were to say that the S represents the orbital, you would be wrong because 2p can hold a maximum of how many electrons? 6, as we mentioned over here. It doesn't have to hold 6, but here need 2 because we're trying to hit 19 electrons. So the p6, definitely p cannot be orbital, because orbital can only hold 2. It's all 3 of them on collective effort, right? Then end up with 6 electrons. Okay, then what's the next one? Okay, then you move on to 3s, s can only go up to 2, then afterwards 3, p, 6. Up until this point, you count, you have 18 electrons. After 3p, you go to 4s. And 4s, you only left with one more, so you don't need to fill it up with 2, you just need to fill up with whatever you need. Right? So that's the idea here. Okay? Okay, D is for anything above 20, transition metals. Yeah, okay, we'll see some of that. In fact, we'll see one of that right now. Okay, so you can take a look at iron on the next page. Okay, so for iron, we have 26, so you have to go a lot more, you have to write a lot more subshells over here. Nice. Okay, so we go through this for the sake of Hilda also. Okay, but over here, we just need to start again with the same order. 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so up until now, we have 18 electrons. Up until here is fine. Okay, the tricky part is what comes after 3p6. What do you fill in first? Okay, according to the Aufbau principle, after this you must fill in with 4s. Maximum we can fill up 2, right? Because we want to try to hit 26. Right? Yeah, okay, so 4s should fill up to 2 first. But then if you follow the diagonal Aufbau principle there, the next thing in line is 3d. Okay, so 3d, how many more electrons do you need to fill up? Okay, right now I have 20, right? So to hit 6, I can write down 3d 6. But you cannot write 3d6 afterwards. You must write 3d6 over here. That's why I left the gap. This part here very important because the unspoken rule is this. Your number must be going upwards like numerically. So I want to see 1, 2, 3, 4 in ascending order. I do not want to see 1, 2, 3, 1, 2, 3, 4 and then drop back to 3 afterwards. Okay, that's the rule when it comes to configuration. But after all this is said and done, at the end of the day, I want to see 4s filled up first and then 3d is filled up next. You just put it here, then put it to the left. Okay, so this right here is a transition metal, yes. So you start to see a D subshell pop up. You won't really go anything beyond this 3D. Okay, of course, it does happen sometimes, okay, but here 3D can hold up to how many electrons? Okay, yes, it is possible for you to go all the way up until 3D10 because of what we have discussed earlier just now. Okay? Yeah. Okay, so there are more examples later for us to practice. But before that, right, I want you to try to write a configuration for iron 3+. So maybe right below it. I know there's no box for this, right? Okay, but try to write for iron 3+. Okay, you just modify a little bit of the thing here. Okay. So what do you get here? What's the rule that I should follow actually? Try to remove my 3 electrons from 3D or from 4s. Okay, no, wrong. He must remove it from 4s. So let me just clear up this misconception. Okay, so the answer here is if you remove 2 from 4s and then the third one from 3D, your answer will be 3D5, and that's it. Can see why? You remove 2 from 4s first, and then the last one, because you need to remove 3 electrons, so it becomes 3D5. So what exactly is the rule here? Okay, so on the left-hand side here, let's take a look. Okay, to summarize, right? If you want to fill up the electrons, you must fill in 4s first, then 3D. If you want to remove electrons in the cases such as this one, where you want to form ions, cations, you also remove from 4s first, then 3D. In other words, no matter what, you remove or fill up, you must take away from 4s first, or you fill up 4s first. Okay, this is in the case of cation, so just bear that in mind for the next page. I think the next page also have more examples. Okay, but at the bottom of this page, we have an exception to all this that we have gone through so far. The exception, let me just write down at the bottom right, is going to be our chromium and copper. Now you need to remember these two elements by heart. Okay, there's a reason why they are considered exceptions in this scenario. Okay, so the reason for that is this. Chromium and copper. Chromium is 24 chromium. If you were to fill up the configuration by yourself, let me just give you a shortcut. You might have seen this shortcut before, but essentially, do you notice for these three examples, I have the first many subshells under 3p6, right? They're always the same. And I sometimes, okay, it'll be very troublesome, right? You have to write these 6 or 5 or 6 subshells, right, over and over again. So what we will do now, right, is to kind of group them up. 18 electrons over here, right, is actually argon. So we can actually express it this way. Okay, we can write the first 18 electrons as argon first. And then after argon, I need to fill up 4s, right? So next is 4s, 2, and then 3d. So this is 20, so it's not 3d. 4, okay, to reach 24, right? However, this is wrong. We can't actually do this because the correct configuration for chromium to be the first 18 electrons, then 4s is 1, then 3d 5. Why is it so weird? Why are you not filling 4s first, then 3d? You haven't filled it up, then you're going to fill in 3d already. Why is that so? It's similar for our copper. Copper is 29, right? Okay, but in this case, if you fill in your argon first, okay, and then you will fill in 4s2, then what's 3d? 3d is 20, 59. Again, this is wrong because we should actually fill in 4s1, and then this one will end up as 10. There's a very good reason for this. Okay, the reason isn't usually tested, but I start to see it more often recently. And let's come up with the reason for this. You can take this down also. Why is it that they don't fill in the full 4s2 and then they go and fill in the 3D subshell? Okay, so let's take a look over here. Now, the reason for that is if we take a look at this first set over here, we will have to understand this thing called electron in box diagram. Perhaps, okay, for the sake of the recording, right, we won't go through this yet. Okay, I will go through how to draw electron in box diagram later on the next page, and then we will come back to why, right, these two guys are preferred over these two guys. Okay, so you can turn over to the next page first. On this next page, we just have practices. So I just need you to fill up all the electronic configurations. Okay, there's the atom first, then the ion. So remember, usually you need to fill in the atom first. Then the ion comes afterwards, where you just remove the correct number of electrons. Okay, or you add whatever. Okay, so give that a try first. Question 2, then we'll go over what electron box is. Okay, let me just write on the board so that the recording can see. Okay, so for atom first, right? Okay, we take a look at sodium. Sodium is 11. Okay, for the atom is until 3s1. For the ion, you just remove the one electron over there, so it's 2p6. Right? Okay, next. Okay, iron 2 plus we already went through already. So the atom is up there. Iron 2 plus will be, let me just write the ion. You will get 3d6. Right? Okay, finally we have Cl minus. So for Cl first, we have 17 electrons. 2s2, 2p6, that's until 10. 3s2, 3p5, so you add another 7. Yep. And then afterwards, here's 18. So you repeat the same thing, but here will be 3p6. Okay. Now, with that said, okay, we will now take a look at electron in box diagram. So this is not really in the notes yet. Okay, so we just go through right now. We can actually express the electronic configuration of all of these guys in terms of an electron in box diagram. How does this work? Okay, so let me just fill this in first. This one 4s2. Okay, now they never specify, okay, they only say it's for the elements. So perhaps, right, we just draw for the atoms over here. Okay, the ions, right, we ignore. We only draw electron and box for these three guys. Now, first of all, right, an electron in a box, what does a box actually represent? Now, the box doesn't represent the electron, okay, but it's to represent an orbital. We come up with the rule first. The one box represents one orbital. So remember the hierarchy, right, of how the atom structure looks like first. Orbital is kind of like the smallest thing that holds the electrons, right? So an example is this. Let's take a look at sodium plus. For sodium, we have 11 sodium. Okay, ignore the plus. So it's this one here. For 1s2, how many boxes must you draw? How many orbitals are there? 1. S subshell has 1 orbital. So this is 1s. Next, S subshell here also has 1 orbital. So 2s. For P, how many boxes must you draw? Yeah. Okay, good, because a P subshell is made up of 3 orbitals. So this is 2p. And finally, we have 3s over here, still made up of 1 box. Now let's just fill in, right? Okay, all the electrons that are inside. In order to fill in an electron, okay, first of all, the rule is if there are 2 electrons here, right, you must fill in 1 up and 1 down. So what's 1 up? 1 up looks like this, 1 down looks like this. Next, 2s also the same thing, 2s2, so 1 up, 1 down. But how do we fill in a 2p subshell? Should we write this? 1, 2, 3, 4, 5, 6. Can we fill in all that like that? No. Okay, how should we fill them in first based on the rule that we learned earlier? Okay, good. You must make sure electrons are alone first. It's like kind of how if you go onto a bus and then the top deck is like completely empty. And then people start coming onto the bus, onto the top deck. Will people start sitting with you? If no, it's empty, right? Everyone will just sit alone first. Because we are all like that. We just don't like sitting with people. Okay? Once it's completely filled already, then who will you sit with? You have no choice but to sit with someone else, right? Okay, so you just have to sit another 6 electrons, so 4, 5, and 6. That's just how buses in Singapore works, right? Then we take a look at 3s. 3s, how many electrons are there? 1. Okay, you don't have to fill up the whole thing. Okay, so that's an electron in box diagram for sodium. Okay, perhaps you can do the same thing for iron. Iron in this case just follow this configuration, or it's right there. Okay, how do we draw iron's configuration? Perhaps for the first 18, right? I think this one should be quite simple. Okay, so 1s2, 2s2, 2p6. Okay, then we continue. We have 3s2, 3p6. Oops, 3p. Okay, but this one, right? Okay, starts to get a bit tricky towards this area over here. Okay, so how many boxes should we draw for a 3D subshell? Remember? Okay, good. So D subshell has all those 5 very funky orbitals, right? Okay, so you just want to draw 5 of those boxes. If this case is 3d6, how will you fill in the 6 electrons?
5.
Okay, good. So you sit them all singly first. But unfortunately, the 6th guy has to sit with someone. And then finally, we have 4s afterwards. Okay, so your 3D still has to come before 4s in an electron box diagram. Okay, so this one is completely filled up. Okay, very good. Okay, so perhaps you want to do the last thing, which is for chlorine. I don't think chlorine is very hard because it's less than whatever we did for iron. Right, okay, so nice. Okay, for chlorine, it's just until 3p5. So your 3p5 here, just make sure it's 2, 2, and then some only have 1. Okay, very good. Okay, so that's electron in box. Okay, can you try the last question? Okay, question 3, where they ask for chromium 3 plus and copper 2 plus. Oh, wait, I still haven't explained that one thing. Okay, before you try question 3, okay, let's try to explain why chromium and copper, the both start with C1, right, are special cases. Why do you fill in 4s1 and then 3d5? So perhaps you want to highlight, right? You can turn over to the previous page still. You can highlight the significance of having a 5 and a 10 over a 4 and a 9. By drawing an electron in box diagram, how will you draw 5 3D electrons? It's just 1 in each box. Okay, correct? Now the thing is, it could have been 3d4, right? But it would rather be 3d5. Now the reason behind that is because having 5 electrons all singly filled like that is kind of like a very nice number, right? This is known as a half-filled subshell or half-filled orbital. Just to make sure you know your terms well. Subshell. Okay, the whole thing is a subshell. Each box is the orbital. Good. So a half-filled subshell, right, actually makes the compound or the atom in general, right, more stable. So the atom is like, I can either be 3d4 and be like, okay, or I can steal an electron from 4s and become even better. Of course, he chooses this. So we will rather sacrifice 1 electron here to make sure they have a very nice 5, very nice half-filled subshell. So that is your explanation. Explanation very short one. Okay, is the real answer is of course way more complicated. Okay, but half-filled subshell makes a compound, makes the atom more stable. On the other hand, why did it make 3d10 instead of 3d9? What's the significance of having 3d10? It's fully filled. Good. So if you draw the electron in box diagram, of course, everything here is fully filled. And once again, for a completely filled subshell, kind of gives the atom extra stability. So both of them have the same ultimate reason, but of course, depending on which guy you explain, chromium or copper, you must choose how filled the subshells are. That's why 5 and 10, at the end of the day, they're just saying that they have nice numbers. 5 and 10 is much better than 4 and 9. 4 and 9 is like almost there, but not there. So they are like not very comfortable with it. Okay, can? And then since we were talking about chromium and copper, you can do the question on page 18. Okay, so if you want to use the Argon method, go ahead. Okay, can also. Okay, or if you want to fill up everything, also can. Okay, so if you want to do chromium 3 plus, you'll be what? Okay, good. So for 1 over here gone, 2 over here gone, so 3d3 actually. I think you made a mistake there. Okay, 3 plus, so you remove 3 electrons. How about copper 2 plus? Again, good 3d9. 1 here gone. Here. Okay, so you still follow the rules where you remove 4s first and 3. Hands over. Okay, this one's just a matter of practice. Okay, so there's enough practice in the notes. Any issues? Okay, if there are no issues, right, we shall take a longer break first. And then later we can go through a little bit of physical trends. We still have another lesson for this. Okay, so we can catch up the next lesson to finish it up. Yeah, okay, this topic generally very short, okay, since you also learned some of this in secondary school. So we can definitely finish this by next lesson. Yeah, so basically by the time school starts, I think it's like what, 3rd Feb, right? Is it? I don't know. After orientation. Okay, let's say after orientation ends. Technically. Yeah, exactly. It's technically the first day of school, but by the time orientation ends, I can say we are about 3 topics in. So don't worry so much.
That's a Friday.
That's a Friday. Let's don't go lah. Okay, see, this started a little bit. Okay, so let's continue a little bit of physical periodicity. Maybe I aim to cover down the group. Okay, then across the period onwards, next lesson we can go through. Okay, but anyways, what we are doing right now is going to be quite different from what we have gone through just now. We have already just now gone through the structure of an atom, so nucleus and the different types of shells and orbitals. But right now, we're going to be looking at some trends to navigate a periodic table. In other words, to read a periodic table, right, there are two different ways. You can either go down the group or you can go across a period. And the thing is, we can use this to explain a lot of different trends. Because in the periodic table, right, okay, we know that the arrangement of the atoms are not just for fun, right? Okay, they actually have some sort of order to it. What is the order? Okay, so let's look at the explanations first. Number one is when you want to go down a group, right? The basis for explaining anything is the number of quantum shells. Okay, you can take note of this first. Okay. In other words, whatever you want to try to explain, whether it is the atomic radius, whether it is the, okay, there are many things that we'll talk about later. Now I say also not very sure. Okay, but no matter what, we have to look at the number of shells. But when you go across the period, right, the number of shells will not change. So we have to look at something different instead. We call this effective nuclear charge. This one we probably will go through in the next lesson. So remember, quantum shells is just the main shell of an atom. Okay, so if let's just say a very easy example is on the next page. Okay, so whatever you see on 19 and 20, okay, effective nuclear charge I'll explain eventually. But not, right now we can go over the 21. There's a lot of blanks, okay, because over here I will now want to explain all about trends. Okay, you will deal with down the group first. Okay, the first thing we're going to explain, right, is atomic radius. What is the trend of atomic radius when we go down the group? Okay, so let's see how we start off our explanation. So, as I mentioned, to start off your explanation, you must look at the number of quantum shells. As you go down the group, what happens to the number of shells? Okay, you definitely have more and more shells, that's why it becomes bigger, right? So you must first tell me that the number of quantum shells increases down the group. So you must specify the direction in which you're navigating the periodic table also, so I mentioned that down the group. But what does this mean? So you think about the valence electrons, what happened to them as you get more and more shells? Further away from the nucleus. Okay, good. So let's mention that first. Okay, because we are talking about atomic radius. Atomic radius is measured all the way to the valence electrons. So valence electrons become further away from the nucleus. And as a result, okay, nothing really to do with that. We just need to look at what we are aiming to explain, atomic radius. So it becomes further and further away, right? What happens to atomic radius? It just becomes bigger, right? Okay, so you can just tell me atomic radius increases down the group. In other words, okay, atoms just become larger in size as you navigate down the group. So this is a very simple explanation, okay, because nothing much over here. But I want to go over the next new concept that we're going to look at. Okay, it's called ionization energy on page 22. Okay, so what is ionization energy? The definition is somewhat there already. But to put it simply, right, ionization energy is the energy needed to pluck out an electron from an atom. Okay, you pluck out electron, I ask you, do you pluck the innermost electron or you do pluck the outermost electron? Okay, because it's way easier, it's weaker, right? Okay, so it's easier. You don't plug the inside one, okay, that one cannot reach. So when we discuss ionization energy, it's called IE for short. We have this thing called first ionization energy. Why is there a first in front? Okay, what does first actually mean? Okay, so let's take a look first. First ionization energy, you want to make a guess? Not exactly, okay, but good guess. Okay, but in other words, first ionization just means the removal of the first electron. So clearly, when you want to remove electrons, there has to be a first electron you want to take away. So when it comes to first IE, let's take a look at an equation that represents the removal of an electron. Okay, without looking at the definition yet, right? When you remove an electron from an atom, you will form a what species? What's the species called? What ion?
Negatively charged.
Negatively charged, sure. remove electrons, so you have less electrons, so you should have a cation, right? So the equation for first ionization energy should be this. Let's just say I have a random element X, okay, and when you remove already, you should have X with what charge? Plus, okay, cation, and then because you remove the electrons, you need to balance the electrons also, kind of like a redox reaction like that. Okay, so if you take a look, there are a few important things. Number one, I have written down the gaseous state symbol because it is just part and parcel of the definition. You can only remove from a gaseous atom to form a gaseous cation. In this case, okay, yes, this is called an atom. It is completely neutral. This one is also more commonly known as a singly charged cation because there's only one plasma, right? And the definition I'm not even going to write on the board because you can actually read the definition and even smoke it out yourself as long as you know this formula over here, this equation. The first IE is the energy needed to remove an electron from 1 mole of gaseous atoms to form 1 mole of gaseous singly charged cations. And that's exactly what the definition roughly says. You can see that? Okay, so they even ask you to, there's a note over there, you must write down the gaseous state symbols if they are asked you, if they were to ask you guys to write down an equation. But the most important thing that I want to talk about, right, is also just highlight out this species over here. What do I mean by this? When you discuss first ionization energy, you must look at the atom itself. It's not the singly charged cation. Reason behind that is because when you remove electrons, you're preparing to remove it from this guy, not this guy. This just happens to be the product after you remove the electron. Okay, you will look more obvious later on. Okay, so just take a look at the next blank box here on the page 22. Okay, they ask you guys to define second ionization energy. We write down an equation first. The definition you can just scoop from the sentence, basically from the equation. Okay, so we take a look at here. Okay, in comparison, what is second ionization energy? To put it simply. Okay, so it's the removal of the second electron. Okay, but a very important question is this. When you remove the second electron, is from the which species that you remove the second electron from? Good. Okay, the second electron is from here, not from here. Okay, so let's come up with an equation first. We remove from the singly charged cation, and then we form a what? We remove one electron, so it's X2 plus. Good. So X2 plus gaseous state, you remove the electron here. Once again, they have their own respective names. Okay, this is a doubly charged cation. You can even use this. Doubly charged gaseous cation. This one is just a singly charged cation. And see that? No? And once again, we are removing the second electron from this guy. So this is the thing that I want to look at whenever you discuss second ionization energy. We'll come to this more in the next lesson also. Okay, but the main idea is when you remove the second electron at time, okay, the definition is pretty much the same. Okay, so you can go write down the definition in your notes also, right? So how do we come up with the definition? Is the
energy required to
okay,
remove
good.
1 mole of electron
Okay.
from 1 mole of singly charged cation.
Okay, to form.
1 mole of doubly charged cation.
Okay, gaseous cation. You must put the word gaseous inside also. Okay, so yes, correct. So always come up with the equation first. This is very, very important. Okay, from 1 mole of singly charged gaseous cation, we form 1 mole of doubly charged gaseous cation. You could also think about it. As you remove more and more electrons, do you think it gets easier or harder? Okay, what? Bonds are strong. There's no bonds inside. Okay, forces of attraction are stronger. Good. But why are the forces of attraction stronger as you remove more and more? As you remove more and more, you eventually get closer to the nucleus. So it just gets tougher and tougher. Okay, we will explain that in the next lesson. There's a box for that, but sometimes it's not as simple as that. Because what if, right? as you remove electrons, does it necessarily mean you are inching closer to the nucleus? What if you're on the same shell, right? On the same shell, let's say you have total of 8 electrons. You remove one already, you're still as far apart as before. Okay, that difference is actually still quite large actually. There's a reason for that, which we'll look at in the next lesson now. But ionization energy, okay, is all about removing. You can go up to 3rd IE, 4th IE, 5th IE, so on and so forth. Why I highlighted the left side of the equations is because a lot of people see first IE and they think, oh, removal, you think of X plus, right? Okay, because first, then they put X plus. But no, I don't care about that. It's from the atom first. So conversely, when they look at second IE, a lot of people think, oh, 2 means X2 plus. No, it's actually one number smaller. So if I were to tell you 6 ionization energy, which species do I actually look at? X5 plus. That's very important for all the questions regarding IE, which we'll practice more in the tutorial. Okay, so that's for ionization energy. We can very quickly finish the one more trend. Then I think we finished down the group. Down the group is very simple because everyone can think about what quantum shells are. The next part of the lesson, which is across a period, that one a little bit different. So we now know what ionization energy is. Let's write down the trend. Okay, what's the trend of IE? What happens to the ionization energy down the group? They say it decreases, right? Okay, again, how do you start off your answer? Okay, good. Okay, so you must first mention down the group, your number of quantum shells will. Good. Okay, so if the number of quantum shells increase, then okay, you can imagine it goes further away from the nucleus, right? Okay, good. So valence electrons, okay, become further from the nucleus. Okay, so
the process of
okay, so good. Okay, so just now you notice, we stopped off our answer there because we wanted to answer atomic radius. Okay, obvious increases, right? However, over here, we can't just end off our answer. We talk about forces of attractions. Good. Okay, they call it electrostatic forces of attractions. But to dumb down your answer, you can actually just write attractions. Attractions between what? Is it just any electrons? And the good. It will decreases. Okay, because it becomes further away from the nucleus, so it becomes weaker in terms of attractions. Why do we discuss attractions? Because here, what's the final point that we need to mention? It is about first ionization energy. So, does it get easier or harder to pluck out the electron?
It gets harder.
Really? Attractions are weaker, so it becomes easier. Okay, good. So now the final keyword here is energy needed. So energy needed to remove the first electron decreases. Long explanations like this, okay, it'll be good to write down the highlight the keywords. Okay, so number of quantum shells is 1. After that is further away. These two words, very important, should always come together. Attractions and energy. Okay. So these are a little bit more than the initial one, because initial one, you don't even have to talk about attractions. And so far. Okay, so that's for down the group. So far, this one's quite intuitive. Next lesson, we'll move over to effective nuclear charge and finish off the topic. Okay, once you finish off the topic, we can just focus on our tutorial solely now. Yeah, okay. So in other words, okay, next week's lesson will be still the same 4:30. Today we started at 5 because of some, you ended late also. Okay, well, 4:30 lah. I know school will start eventually. Okay, and when let's say your school's timetable does clash for J1 shouldn't be an issue, and someone you're taking PCME, so shouldn't be that bad. Yeah, your timetable should usually end quite decently early, unless your Thursday suddenly got CCA, unless they end very late or some stuff like that. But if there's none of that, right? Okay, then we will just continue with Thursday 4:30. Yeah, I'll be seeing Chloe tomorrow also. So I'll catch her up with the redox stuff. Yeah, still catch up with the atomic structure stuff. Yeah, so it'll be a while before I can replace both of you guys together. Yeah. In where? Like secondary school, right? Okay, so I think it'll be quite fast. I can catch up with her quite quickly. It's the redox stuff that's more important. Yeah, so once that's all caught up, then you guys can finally sit together. Yeah, okay, can. So that's it for today.